Okay, in this video, we want to derive a logarithmic expression for the inverse hyperbolic cotangent of x. And before we do that, well, we'll talk about these curves here in a second, but remember now how we have this set up. If the inverse hyperbolic cotangent of x, if we set that, say, that's going to equal y, that's the same thing then as saying that the hyperbolic cotangent of y, that has to equal x. These are two equivalent expressions here. Now, over here in blue, we have sketched out the hyperbolic cotangent function. And here we have, as we did before, this is in general what the hyperbolic tangent looks like. It approaches a maximum value of y equals plus 1 and a minimum value of y equals negative 1. Let's look at this side of the curve. Here, y is 0 for its, and this right here, of course, is the reciprocal of this. So if y is 0 for its reciprocal curve, we would expect y to be approaching infinity. Then as this approaches plus 1, its reciprocal curve is going to decrease to plus 1. So the general shape of the curve is what we would expect. Now over here, now the hyperbolic tangent, it has its minimum value of negative 1, and the reciprocal of that is negative 1. And then as this gets less and less negative and starts to approach 0, this is going to get more and more negative and approach negative infinity. For example, if this becomes, say, minus 1/2, the reciprocal of this would be minus 2. If this is minus 1/3 now, then the reciprocal of that would be minus 3. So as this starts to approach 0, this here is going to go out to negative infinity. So again, the general shape of the hyperbolic cotangent is what we would expect it to be. Now here we have the inverse hyperbolic cotangent here and here, and then in black we have what we've done before in previous videos. This is the inverse hyperbolic tangent. X has a maximum value of, it approaches the maximum value of x equal to 1, and here it approaches the value, its minimum value of x equals negative 1. So for here, for x equals 0, for its reciprocal curve, we would expect that to be out at infinity. And then as this approaches plus 1, its reciprocal curve is going to decrease to the value where x equals plus 1. So again, the general shape of the curve is what we would expect it to be. Now over here on this side, here the inverse hyperbolic tangent, when it's down here at its leftmost asymptote, where x equals negative 1, its reciprocal curve, it's also going to have negative 1 for its x value. But now, as this starts to approach 0, and then say we're here at negative 1/2, this would be negative 2. As this gets to negative 1/3, this would be negative 3. As this gets to minus 1/4, this gets to be negative 4. So as this approaches 0, its reciprocal curve is going to be going out to minus infinity. So again, this would be the general shape of what we would expect for the inverse hyperbolic cotangent. One other thing to notice, here the absolute value of x for the inverse hyperbolic cotangent, that's always greater than 1. Over here, it's always less than negative 1. Okay, let's see then. We want to get a logarithmic expression for this, and to do that, as we've done in the other videos, we start by working with this expression here. So we have hyperbolic cosine divided by the hyperbolic sine. So we have e to the y plus e to the minus y divided by e to the y minus e to the negative y equals x. We'll multiply through by this, and we'll have e to the y plus e to the negative y will equal x times e to the y minus e to the negative y, or that would be 1 over e to the y. So this will be equal to x e to the 2y minus 1 divided by e to the y. Or we can multiply both sides of the equation by e to the y. So here then we would have e to the 2y plus, that would just be 1, and that will equal x e to the 2y minus x. And let's see, here we have e to the 2y, and here we have e to the 2y. So let's bring this over to here, and we will have e to the 2y times 1 minus x will equal, and we'll take this over here, that will be minus 1, minus x, we can say minus x plus 1, or e to the 2y that will equal minus x plus 1 divided by 1 minus x. Or we could say, multiplying through by negative 1, that would be 1 plus x divided by x minus 1. So nothing tricky here. Well, let's just pause for a moment. Now, remember, e to the y is always positive, so e to the 2y is always going to be positive. And remember also now, for the inverse hyperbolic cotangent of x is always greater than 1, and it's always less than negative 1. So let's check this out first. We had these from the curve up there, here and here. Now, x is always greater than 1. So here then, I'm subtracting 1, but x is always greater than 1, and it's always positive. So this will always be positive. That's not a problem. But what about here? X is always less than negative 1. So up here, that's going to make the numerator negative. For example, if I had negative 2, I'd have 1 plus negative 2, which would be negative 1. So here, for this, the numerator is always going to be negative. Now what do we get down here? Well, here we have a number smaller than 1. For example, it could be negative 2 minus 1. So here we're going to have two negative numbers added together. That will also give us a negative number. So the denominator is also going to be negative. So for this here, this also gives us a positive number for our e to the 2y. So for the values that x exists in, for the inverse hyperbolic cotangent, e to the 2y will always be positive with this expression here. So that won't give us any problems. So let's get to the end here. we can take the natural log of both sides, and we'll have 2y will equal the natural log of x plus 1 divided by x minus 1, or y will just equal 1/2 of that. Or, based upon our property of logarithms, we could say that this would equal the natural log of the square root of x plus 1 divided by x minus 1. Remind ourselves now, x is always greater than 1, or x is always less than -1. Okay, so going back to here, y is this, so we can say then this is equal to the natural log. Let's just make a little bit of room here. The square root of x plus 1 divided by x minus 1. And remember, x exists in these ranges here. Okay, that's it then. That should pretty much settle it for the inverse hyperbolic cotangent. And we have other videos now. We have one video where we take the derivative of the hyperbolic tangent of y using its basic definition. That's a little bit of a workout, so we did that. And then we have other videos where we take the derivative of the inverse hyperbolic functions. So come back and join us for those, and we'll see if we can work some more problems.